Great. Yes, thank you for the introduction. Yes, so like Miho said, I'm going to be talking about the way in which we've in the past used Parker Solar Probe and Solar Orbiter together to really answer some big outstanding questions about solar physics, and also why it's really exciting right now to be a solar physicist and do some of the solar science. So as you know, and you've heard through the course of the different webinars, uh, s- um, Parker Solar Probe and Solar Orbiter are orbiting the sun right now. Solar Orbiter carries this very comprehensive set of both remote and in situ observations, instruments that provide these different kinds of observations. Solar Orbiter gets to its closest approach is roughly about the orbit of Venus. Parker Solar Probe gets a bit closer. Um, since its launch back in 2018, Parker Solar Probe, its closest approach has gone from about 30 solar radii. The last two orbits, Encounter 23 and 24, have been at 9.8 solar radii, so very, very close to the sun. But together, they cover the heliosphere quite well. So this is a movie showing, I'm just going to move the camera a little bit. So this is a movie showing the trajectories for a period, for a time frame back in 2024 from February to about April um, of 2024, showing the trajectories of both Parker Solar Probe and Solar Orbiter. This period actually covers the total solar eclipse that happened over North America back in April 8th, 2024. So you can see both Parker Solar Probe going into perihelion for Parker Solar Probe starting at 0.25 AU, so roughly about 54 solar radii, getting to its closest approach. In both cases, Parker Solar Probe and Solar Orbiter going to closest approach that I've highlighted here. And so you can see in this time frame, right, for this particular encounter in perihelion, and all of them are very unique, so I implore you to go and take a look at those. But you can see them often intercepting a very similar part of the heliosphere and often the same solar wind streams at different locations in the heliosphere. So these specific spacecraft lineups are ideal, these conjunction periods are ideal for examining the radio evolution of both coronal mass ejections and the solar wind, looking and understanding the radio evolution, longitudinal and perhaps also the latitudinal extent in the future as well of energetic particles. So I'll give you some examples of that later on. I mostly work in the solar wind, so my examples will be in the solar wind, but there are some wonderful examples of this with transients, with coronal mass ejections and energetic particles. One thing I did want to mention is that if you are interested in any of the plots or the videos that I'm showing, most of them are created by me. However, I haven't quite gotten them up to on GitHub just yet, haven't gotten to that point yet. But if you are interested in recreating them, do email me. I'm happy to share the code so you can do that. So I thought because the webinar so far is focused on on Solar Orbiter, I thought I would focus a little bit more on Parker Solar Probe and its unique orbit and some of the caveats associated with going into perihelion. So like we talked about before, Parker Solar Probe has very similar instrumentation to Solar Orbiter. It measures the fields, electromagnetic and magnetic fields, the properties of the plasma, temperature, density, and velocity, energetic particles. It also does carry a remote sensing instrument. This is WHISPER. This is the wide field imager for Parker Solar Probe. So in this case, the images are taken not directly of the sun, but the heliosphere during perihelion time. I've also listed there, all of these data products can be found at CEDAWeb, which is hosted by NASA, also institutional websites that I've linked here. And I think you'll have the access to the slides so you can take a look at those. But you may wonder, so I wanted to focus on SWEEP. There are three instruments associated with the SWEEP suite. The Solar Probe Cup, which is a Faraday cup, which faces forward, kind of peeking outside of the heat shield. There's also SPAN A and SPAN B instrument that measures ions and electrons. And you may wonder why there are two instruments on Parker Solar Probe that measure ions, so protons and helium as well. And the reason for that is because of the orbit of Parker Solar Probe. So as Parker goes into perihelion, its spacecraft velocity is very comparable to the solar wind speed. Its tangential velocity is so fast that the flow of solar wind actually changes from going into the front-facing SPC instrument into the side view of SPAN. So SPAN is here. span is here, facing to the side of the instrument. And the reason for that, that's having both these instruments really by design. So here is a plot back from the 2016 paper for SWEEP. So you can see the red curve shows the detection of proton core for SBC going down as the proton core is being more measured going into the field of span. And so together, again, by design, this is meant to measure the full properties of the solar wind across this perihelion period. But going into, the field of view of span, you still need to consider during these perihelion times, you still need to consider the measurements taken by span during its closest approach for two different reasons. One is that the span field of view is actually partially blocked by the instrument, by the heat shield. So I've made a plot here of the distribution of protons as measured. So in the azimuthal direction, in this plot here, so in the horizontal direction, and then at different elevation angles here. So this is a plane perpendicular to the phi angle. So you could see the field of view of span is partially blocked here. The second thing is you often have to contend with the velocity distribution functions of both the protons and the helium going in and out of the field of view of span during these periods. And the reason for that is because you have these big alphanic fluctuations, these switchbacks that move the PDF out of the field of view. So this is a video actually showing this in action. So I'm showing the velocity distribution functions up top, the proton density in the middle, and then the field of view again in the azimuthal flux. So you can see at the beginning, you start with a density that's roughly about 1,000 cc's that drops down to 0. All of these are the reason for these dropouts are because of the velocity distribution function moving out of the field of view. So I'll show you again. So you can see the velocity distribution function is really not in the field of view. So this is not a change that happens in the plasma, but rather an artificial dropout of these densities. So something to think about when using the span instrument. And I've also included here a couple of links that help you plot. So simple plotting of the data. So this is for span I, span E, looking at the electron straw if you want to take a look, and also the instrument paper if you want more details on the span instrument. So I also wanted to highlight an instrument on Solar Orbiter, the heavy ion sensor that is part of the Solar Wind Analyzer suite. So of course we know that Solar Orbiter carries a suite of remote sensing instruments that is unique to Solar Orbiter that both images and takes spectra of the sun and its surrounding atmosphere, but it also carries, and this is unique to Solar Orbiter, the heavy ion sensor. The heavy ion sensor measures the thermal population of heavy ions in the solar wind. So this would be carbon, oxygen, iron, and other elements as well. And what's really useful and important about measuring heavy ions is although they are measured locally in wherever the spacecraft is in the solar wind, it's actually a lens back to the corona. So the measurements that you take, the ions, the elemental composition can tell you about the temperature and magnetic topology of where the solar wind came from back to the sun. So incredibly useful to linking the structures in the heliosphere back to the sun and understanding aspects of their formation, for instance. And so with both Parker Solar Probe and Solar Orbiter, not only can you link measurements, in situ measurements at both these places in the heliosphere, but also to the sun. So as I'm showing here, this is an example of actually related to the movie or the time frame in the movie. So in the first slide, this is the trajectory of Parker Solar Probe and Solar Orbiter during that time frame, sampling the solar wind at these different locations in the heliosphere through this ballistic mapping that has been historically done during the two missions. You can actually link a lot of the structures back to what's called the solar surface. The solar surface typically taken to be roughly about 2.5 solar radii, linking these structures to each other. And through this ballistic mapping, this then allows you, coupled to a coronal model of the magnetic field, for instance, in this case, a PFSS model that I'm showing here, the foot points can be associated with photospheric location on the sun as you link these two. So this is just showing an example of that. I've also included here a link that's really handy showing this BFSS model. So again, projecting these along these Archimedean spirals and also linking them to this to different places on the sun. So that's really handy. So from the measurements of these two spacecraft, you can use, for instance, the polarity of the wind to confirm the mapping that you've done. And also, of course, looking at the solar wind at two different phases of its evolution. So here, I've plotted then the properties associated with these two spacecraft sampling the solar wind at two different locations. In particular, I wanted to just share, right, this is really an opportunity. I've included the same properties across the different panels. This is the Mach number showing that for the period sampled by Parker Solar Probe, you are largely subalfanic for a large part of its orbit within this region that I've sampled here, and you're mapping that to a very super alphanic part of its evolution, which is really unique and really exciting. So what I've done here is I've listed several of the studies that really capitalize on using both Parker Solar Probe and Solar Orbiter during these conjunction periods, which is often what I do. But also I wanted to highlight some of them which have really used this quadrature configuration mapping structures observed by METIS, the coronagraph on Solar Orbiter, to then measurements, in situ measurements of Parker Solar Probe, specifically a lot of work by Danielle Taloni in this paper by Laxman Adhikari, both make use of actually observing the corona and then sampling it with Parker Solar Probe during these quadrature configurations. So next, I just wanted to go over a couple of papers that I just wanted to highlight that make use of both Parker Solar Probe and Solar Orbiter. The first one is a paper that was published back in late of 2024. This paper, again, made use of this conjunction between Parker and Solar Orbiter, looking at the evolution of magnetic switchbacks, these big, large amplitude alphanic fluctuations observed by Parker Solar Probe in the context to understanding the role that they play in the energetics of the solar wind, showing that indeed they were incredibly important and necessary to show and understand the heating and acceleration observed within this fast solar wind stream. So the paper, so I've shown a plot like this in the past. So this is the spacecraft lineup. This happened back in February of 2022. This is during Encounter 11 for Parker Solar Probe. So far we've talked about the lineup that happens in longitude, which is very common. In this case, this is a very special lineup that we had because there was a lineup not just in longitude, as we see here, but also in latitude. So this is Parker's orbit going into perihelion down to a heliographic latitude of -4, and then this is the orbit of Solar Orbiter. So you can see this was a spacecraft lineup that allowed us to sample the solar wind at the same longitude and latitude in this case. So what we were able to do is then measure the properties at these two locations quite well of the same solar wind stream. Of course, so this is showing the temperature as a function of distance and also the velocity as a function of distance during this period. We were able to show that this non-adiabatic cooling of the temperature, which is what we'd expected. And the main takeaway of the paper was when we solved the Parker Solar Wind solutions using this framework, we found that in order to describe the full acceleration of the solar wind in our momentum equation, we really needed to include the contribution from the thermal pressure gradient coming from this non-thermal or this non-adiabatic cooling profile with the addition of the wave pressure gradient that we were able to measure using the spacecraft. Which allowed us to really show that the switchbacks themselves were energetically important in the solar wind evolution for this fast solar wind stream. In a similar way, so this is the same conjunction that I was showing in the previous slide. So this is another paper where we made use of measurements, again, taken by Solar Orbiter, heavy ion measurements, and having the benefit of having Parker Solar Probe really close to the sun. So I've made this cartoon picture up here. This is Parker Solar Probe at 13 solar radii. This is a location in which, in this very young solar wind, we can identify this coherent, well-organized switchback patches that we see with Parker Solar Probe, often during perihelion. That solar wind can then be mapped to solar orbiter, and we can make use of the heavy ion sensor to measure the heavy ion composition to tell us about where these switchbacks, or at least the solar wind in which the switchbacks were embedded in, came from the sun. And so we were able to do that in this case for a very large range of longitudes and different types of solar wind with a current sheet in the middle, or a current sheet crossing in the middle. So we were able to sample ion ratios, which tell us about and can be linked to coronal temperatures back at the sun, and also the iron to oxygen composition, who is corresponding low FIP enhancement, can tell us about indirectly about the magnetic configuration and morphology of where the solar wind came from. Ultimately, together, we were able to show that the solar wind in which the magnetic switchbacks were embedded in were coming from the coronal hole, the boundaries of these coronal holes across this entire period. And I also wanted to highlight another paper that made use of the heavy ion sensor as well, focusing on using the heavy ions to tell us about linking to the young solar wind measured by solar orbiter, but also to the source region itself, which is also really interesting. And then the last paper that I wanted to highlight was, again, during this conjunction period, this was a paper that was recently published, so hot off the press. This was a graduate student at the University of Alabama, Ashok Sowal, that published a paper looking at the radial evolution of solar wind turbulence. So again, making use of these conjunction periods, having Parker Solar Probe close to the sun, solar orbiter far away. The main takeaway of the paper was that looking at the power spectrum of the same solar wind, you can actually identify the changes of the power spectrum from one location to another. And also the paper itself looked at the multifractality or intermittency of the evolution of the solar wind from one place to another. We find that the structure of the power spectrum changes as a function of distance. So you'd expect it to go into lower frequency, which it does, but also the profile of it changes as a function of distance, and also that the multifractality weakens as you get farther and farther away from the sun in this slow wind stream. There are a couple of other papers that have also looked at this, Taloni 2021 paper, and then this Perron 2022 paper, which are very compatible and complementary to some of the observations that we see here. And lastly, I just wanted to kind of emphasize this partnership between Parker Solar Probe and Solar Orbiter. This is a very exciting time to do solar physics. Again, Parker Solar Probe's proximity to the sun really allows you to capture this newly formed young solar wind, the properties and its state. Solar Orbiter observes the sun and its atmosphere directly, allowing us to link this very young solar wind measured by Parker Solar Probe to the sun, and also provides an opportunity to measure the in situ properties at a later stage of its evolution farther away from the sun. So together, these two missions and the observations that they take are really revolutionizing the way that we observe the sun, right? It really allows us to understand where the solar wind originates from, how it's formed, how it evolves through space, and really providing an opportunity to address some of the outstanding and these big fundamental questions in solar physics. Again, so I just wanted to emphasize that if you are interested in any of the plots that I was showing above, I'm happy to share the code to do that. So I will end here and take any questions.
Great, thank you so much. I'm just going to stop the recording.